All right, so for this lecture, we're going to be looking at some other variables that affect gas pressure. We talked in this last one about how temperature affected it. And we know that temperature is measured in Kelvin. And today we're going to be looking at how volume of the container can affect gas pressure. So we would measure volume in liters, and how the number of molecules can affect pressure. And we'll be referring to that in moles, or an Avogadro's number, right? Do you remember that there's 6.02 times 10 to the 23rd molecules in a mole of gas? So the more molecules or particles that we have and how that affects gas pressure. So we are going to be talking about molar volume. And molar volume is what we're going to be referring to. The STP is standard temperature and pressure. Standard temperature is at 0 degrees Celsius, which is 273.15 Kelvin, right? Those are equal to one another. And standard pressure is 1 atmosphere, which is equal to, remember from the last lecture, 760 millimeters of mercury, or there's a whole slew of other units that 1 atmosphere was equal to. But anyways, these are standard temperature and pressure. It's at 0 degrees, so at sea level, 1 atmosphere, 0 degrees Celsius, and we are told that at standard temperature and pressure, 1 mole of any gas occupies 22.4 liters, and that is called molar volume. That could be 1 mole of hydrogen gas, 1 mole of helium gas, 1 mole of oxygen gas, 1 mole of carbon dioxide gas. 1 mole of any gas occupies 22.4 liters. Now, 1 mole of any gas is also equal to 6.02 times 10 to the 23rd molecules of gas. So we now have a new equality, or a new conversion factor, because if we know that 1 mole of gas is equal to 6.02 times 10 to the 23rd molecules, we knew that from this last unit. We also know that 1 mole of gas is equal to 22.4 liters. So we can say 1 mole is equal to 22.4 liters of gas. Again, this is gas. This is not for solids or liquids. Or we can also say that there's 22.4 liters in 1 mole. So that will be a new conversion factor, a new equality that we can use when talking about gases. So if I asked you to find the volume in liters of 0.275 moles of nitrogen gas at standard temperature and pressure. So if I'm given moles, 0.7, so if I'm given moles, I know, again, that 1 mole is equal to 22.4 liters. And again, I need to make sure that moles and moles are diagonal from one another so that they cancel out. So now we just need to plug it into my calculator and do 0.725 times 22.4. And we look, I have 3 sig figs here. So I need to have 3 sig figs for my answer. So it should get 16.2 liters of N2 gas. And circle my answer. So for this next one, there was a typo. This should be liters. How many moles is in 17.26 liters of carbon dioxide at STP? So I want you to tell me moles, and I want to know how many molecules this is. So why don't you pause the video and see if you can work this out. All right, hopefully you set up, again, what do I want? I want moles. So moles is on top. What have I got? I've got liters, so that my liters and liters will cancel. And we should get, again, looking that I do have 4 sig figs here, 0.7705 moles of CO2. And then to get to molecules, I'm going to start with my moles that I'm given, my 0.7705 moles, and I'm going to convert from moles to molecules, knowing that 1 mole, and have moles on the bottom, is 6.02 times 10 to the 23rd molecules. And I'm going to write all of molecules because if I abbreviate it, it kind of looks like moles. We don't want to be confused. So do the plug and chug, 0.7705 times 6.02 times 10 to the 23rd. And again, with 4 sig figs, we should end up with 4.639 times 10 to the 23rd molecules of CO2. Make sure you give a complete answer and circle it. Okay, now, gas density. The density of a gas is directly proportional to its formula mass. Again, notice that I had that molar volume wrong. These all should be 22.4 liters. So, one thing that I want you to see is that all of these gases have 22.4 liters per mole as STP. All of these gases, for 1 mole of these gases, for 1 mole of it, all have 6.02 times 10 to the 23rd particles. Because for 1 mole of anything, there's always 6.02 times 10 to the 23rd particles. And for 1 mole of any gas, there's always 22.4 liters of molar volume. Now, notice what is different, the formula mass. So, notice that I have H2 for hydrogen is 2.02 AMUs. For water, H2O, my formula mass, and this is going back to the periodic table to see what 2 hydrogens and 1 oxygen together have a mass of. Same with N2, 22 nitrogens is 28.14. So notice that my formula mass is increasing with this table, which is essentially telling us that the density is increasing. So remember, the density we just said was directly proportional to its formula mass. The greater the formula mass, the greater the density. Because if you think about it, let's say I have 3 containers that are exactly the same. This one's H2, this one's, and we're also going to use carbon dioxide here. So let's say that this one's N2 and this one's CO2. So my hydrogen, let's say I've got 1 mole of it. Okay, so let's say I have 6.02 times 10 to the 23rd. We're just going to put 6 particles in here though. 3, 4, 5, 6. My hydrogen mass is 2.02 AMUs. So my density is very low. I still have the same amount of hydrogens as I do for nitrogens, but for nitrogens, notice my mass is larger. So I'm going to have my N2s are going to be slightly bigger. Instead of only being 2.02, these ones are 28. So this is 28.14 AMUs a piece. So they're bigger than my H2s, which is 2.02. So these are much smaller. And then I go to my CO2, and my CO2s, wow, they're at 44. That's almost double. So 1, 2. So I still have the same number of particles in each one of these boxes. Same size boxes, right? Same size boxes, same number of particles, but look at the density, and we can see that the CO2 at 44.01 AMUs is a lot denser than my H2. Just look at the size of these particles. It would be like if I said I had 6 basketballs in a container versus in another container I had 6 marbles. I still have the same amount. I have the same number of particles. I'm in the same space, but my mass is different. So therefore the density would be different. I wanted to share this quick video. It's less than 4 minutes, where this guy talks about the density of carbon dioxide in a lake when this lake has an explosion. So if you have 3.5 minutes, I would suggest watching it because it is very interesting and real life, it happened. But you can also skip forward if you want to move on to the next part. But like I said, it should be about 3.5 minutes.
In the evening of August 21st, 1986, 80 million cubic meters of carbon dioxide gas suddenly erupted from Lake Nyos in the West African country of Cameroon. This massive cloud expanded at 50 kilometers an hour, suffocating everything within a 25-kilometer radius, killing more than 1,700 people. The only known similar event happened at nearby Lake Manoon 2 years earlier, where 37 people died. And scientists weren't really sure at first what was going on. They figured these were some kind of volcanic eruptions because both lakes are close to Cameroon's Oku volcanic field, which includes 4 major volcanoes. But even though volcanoes were partly to blame for these explosions, it turns out that they were no volcanic eruptions. Instead, what made these lakes explode were limnic eruptions, which are like popping open the largest, most pressurized soda can of all time. The volcanoes near the lakes are a sign that there's magma or molten rock close beneath the surface, and magma releases huge volumes of carbon dioxide, which can filter up through the crust of the earth into the bottoms of the lakes. Now, these lake bottoms are highly pressurized and very cold, which is exactly what gases need in order to dissolve in water. So lots of carbon dioxide can dissolve in the lakes and just build up, sitting there. But as the CO2 continues to build, those lakes get to be like cans of soda pumped up with way too much fizz. Most lakes don't explode, thankfully, even if they're sitting on top of a whole lot of magma. That's because the water gets mixed around when the temperature changes throughout the year. In the fall and spring, the changing surface temperature affects the water's density and keeps it circulating, and in turn helps release the gas. But in Lake Nyos and Lake Manoon, things are very different. It's hot pretty much all the time, so the shallower, less dense water stays at the top of the lake, where the gas-infused deeper layers stay below. As a result, tens of millions of cubic meters of carbon dioxide can accumulate. No one's sure what exactly triggered Cameroon's limnic eruptions, but a seemingly minor event that another lake might not even notice, like a heavy rainfall or a landslide or a small earthquake, could send some of that gas-rich deep water up into the shallows. In which case, it's like poking a hole in that overpumped soda can and suddenly everything is covered in liquid and fizz. Except that instead of getting a little sticky, the liquid is a 25-meter wave of water and the fizz is a giant deadly cloud of carbon dioxide. For obvious reasons, no one wants this to happen again, so once scientists figured out what was going on, pipes were installed in the depths of Lake Nyos and Lake Manoon, allowing the carbon dioxide to escape before enough of it built up to cause another explosion. Now, though, there's concern about a third lake, Kivu, on the border of Rwanda in the Democratic Republic of Congo. It also has a lot of gas buildup, and the sediment at the bottom of the lake contains evidence of sudden lake-wide extinctions every few thousand years, probably because of limnic eruptions. Lake Kivu is extra dangerous, though, because it also contains enormous amounts of methane produced by bacteria that ingest the carbon dioxide. If that lake explodes, there could be both fiery explosions and widespread suffocation, and there are 2 million people living on the shores of Lake Kivu. So in 2011, plans were put into place to start siphoning off some of that methane and using it to generate electricity for Rwanda. The hope is that we can harness the terrifying power of limnic explosions before they can occur, maybe even put it to good use. Thanks for watching this SciShow Dose. Isn't the world fascinating? Thanks especially to our latest president of space, Matthew Gass.
So what I thought was really interesting about this is just right back here, that carbon dioxide and methane, we can see the density of those gases is obviously greater than H2O. And so the density of those gases were just very, it's just greater. So they're down here and piling up. And it just was really amazing that the volcanic eruption, what did they say, 25 kilometers? I'm trying to go back here. 25 kilometers, which a 5K is 3 miles, so affected 15 miles of area. Here we go. Suffocating everything within 15 miles. I also wanted to share one more little excerpt about this lake and why it's the deadliest in the world. I thought this also had some good information to share.
In the world, which is actually located here in Africa between the Democratic Republic of the Congo and Rwanda. This is Lake Kivu, and if you look at pictures of it on Google, it doesn't really look all that dangerous, so what gives? It's kind of a big lake, I guess. It's the 9th deepest lake in the world too, but that means that there's 8 more that are even deeper. There's other lakes like this one that's literally called Boiling Lake because the temperature can get up to 92 degrees Celsius. So what makes the innocent-looking Lake Kivu so dangerous? It probably has something to do with the fact that the lake seems to occasionally explode and kill everything around it. But how does that happen? A lake exploding sounds pretty weird, but it's because it doesn't happen very often. The first time in recorded history that we observed something like this was just back in 1984 at another African lake here, Lake Manoon. On August 15th of that year, local people reported hearing a loud noise and seeing a gas cloud emanating from the lake. 37 people ended up dying with reports of skin discoloration, which led investigators to initially believe that the incident was a terrorist attack. But 2 years later, the nearby Lake Nyos experienced a very similar but even more catastrophic event. Here's what really happened in both cases. The lakes were completely saturated with gases like CO2. This CO2 may have come from volcanic gas below the lakes or from the decomposition of organic materials, but the end result of a high concentration of the gas in the water is the same. Before the lake becomes saturated though, it behaves much like an unopened soft drink, meaning that the CO2 is dissolved in the water. In both the lake and the soft drink, CO2 dissolves much more readily at higher pressure. This is why bubbles in a can of soda form only after the can is opened. The pressure is released and so the CO2 comes out of solution. In the case of lakes, the bottom experiences way higher pressure than the surface. The deeper it is, the higher the pressure at the bottom is. This means that huge amounts of CO2 can be dissolved in large, deep lakes like both of these were. CO2 also dissolves much more readily in cooler water, like at the bottom of a lake. So once a lake is saturated with CO2 like this, it becomes extremely unstable. All it takes is a trigger event like a volcano, earthquake, or explosion to set the whole thing off. Whatever the cause, the trigger event pushes the saturated water higher into the lake where the low pressure can't keep the CO2 contained anymore. Bubbles start forming at the surface, a column of gas erupts on top, the water at the bottom is pulled up by suction which causes a runaway loss of CO2 and an eventual explosion. Imagine shaking a can of soda and opening it, but on an epically bigger scale. At Lake Nyos, this event happened in the middle of the night and sent a 25-meter high tsunami surging into the other side of the beach. The lake turned a deep red and a 1.2 cubic kilometer toxic gas cloud of CO2 started migrating off the water and into the nearby villages. Because CO2 is denser than air, it has a bad tendency to stick to the ground while pushing breathable air up. As a result, when the cloud entered the surrounding villages, people couldn't breathe and experienced severe CO2 poisoning. Nearly everyone around the lake that night died, and people as far away as 25 kilometers even suffered from it. In all, over 1,700 people lost their lives in the catastrophe, as well as thousands of cattle and wild animals. But as bad as all of that was, the potential for the same thing happening at Lake Kivu would be a lot worse. These lake explosions are called limnic eruptions, and Lake Kivu has the exact same symptoms that the previous two lakes had. The only differences are that Lake Kivu is a lot bigger and has a lot more gas built up inside of it. 65 cubic kilometers of methane and 256 cubic kilometers of CO2. 2 million people live around the shores of the lake, and if an eruption were to happen here, all of their lives would be in jeopardy. Even creepier though, geologists operating around around the lake discovered evidence that suggested a local extinction event happens about once every 1,000 years that wipes out a large part of the local wildlife. If it's the lake exploding once every 1,000 years like it seems, well, that's pretty bad news. So what are we doing to fix this problem? Not really anything at all right now. The Rwandan government extracts a lot of methane from it for energy purposes, but it's probably not enough to guarantee that the disaster won't ever happen. At the first two lakes I talked about, they've installed a series of pipes to release the gas above the surface, but since Lake Kivu is so much bigger, that may not be as practical. Releasing that much gas would be 2% of the annual amount humanity releases from burning fossil fuels, and it would cost millions of dollars to do, which the neighboring countries may not be so willing to spend. The solution to the most dangerous lake in the world remains elusive, and with no clear answer in sight, it may only be a matter of time until another disaster happens. If you want to be the one to come up with the answer, you can mention it in the comments, but before you do, you should probably learn a bit about physics and chemistry by visiting the courses over at Brilliant.
There you go. So if you have an idea of how to solve that problem, we've got a job for you. I love it. Okay, so let's look at one of these application problems now. Not ozone, that should be carbon monoxide. Carbon monoxide and radon are two potential harmful gases found in your home. Determine the relative density of these gases to air. If this gas was in your house, would it be more toxic in the basement or upstairs? Well, so if we look at carbon monoxide, which is CO, we need to look at the periodic table and figure out what the mass of carbon monoxide is, or of carbon and oxygen. Well, carbon has a mass of 12 AMUs, plus oxygen, which is 16 AMUs. So that would give us 28 AMUs for carbon monoxide. And then if we look at radon, if we find that on the periodic table, radon's mass is 222 AMUs. And so if we think about air, right, look at these densities compared to air. Air is almost 80% nitrogen and a little over 20% oxygen. So if we look at nitrogen, which is N2, that has a mass of about 28 AMUs. And oxygen, O2, 16 and 16 is 32 AMUs. So if we compare 78, 88, 98, almost 99% of our air, because we said this is our air composition, 99% of our air, we can see the density is between 28, 32. So carbon monoxide's density, about 28, is right in the midst of all of that. Do you think if this gas was in your home, would it be more toxic in the basement or upstairs? Definitely upstairs. I mean, where is your air? I mean, it could be anywhere, really, anywhere where the rest of air is in your house. But if we look at radon with a mass of 222 AMUs, it is much more dense, much bigger than 28 and 32 AMUs. So it is much more dense, meaning that's going to be in your basement. So that definitely would be more toxic in the basement. Your carbon monoxide, I mean, could be in the basement for sure, but it could be anywhere else in the rest of your house too. All right, moving on, looking at Dalton's law of partial pressure. So looking at partial pressure here, what's important to see is that pressures are additive. And if I have a pressure here, both of these, by the way, it is important to see that they are both 1 liter flasks. So I am looking at same volumes of two different pressure systems. So in this first pressure system of nitrogen, also both at 25 degrees, I have a pressure of 186 millimeters of mercury. And so we're going to call this P1. And in my second pressure system, we're going to call this P2. I have 93 millimeters of mercury. And we see here that they are going to mix. Now, it is important to say that they mix. They're not going to react. I have two inert gases or unreactive gases. I have nitrogen and I have oxygen, and they are going to mix. So we're not going to make nitrous oxide. No, we're going to have a container that has nitrogen and oxygen both in it, bouncing around, moving around. So we're not reacting, we're not having a chemical reaction here, we're just mixing them. So what Dalton's law of partial pressure tells us is that I can simply take my pressure 1 and add it to my pressure 2 to get my total pressure. So I'm going to take my 186 millimeters of mercury plus 93 millimeters of mercury and get 279 millimeters of mercury. And finally, another application problem. At STP, so standard temperature and pressure, what is the contributing pressure of each gas shown in the image below? Okay, so remember, we said standard temperature and pressure was, standard temperature is 0 degrees Celsius, and standard temperature, oh, I'm sorry, that was standard temperature. Standard pressure is 1 atm, 1 atmosphere. We also know that 1 atmosphere could be 760 millimeters of mercury, 760 torr. We could go to pounds per square inch, but 1 atmosphere is just, let's be honest, it's the easiest one to use right now, and so let's use that. So we know that in this image, this is a whole unit, a whole. So we want to know the contributing pressure of each gas if this whole thing is 1 atm. So remember, in order to do that, I need to take pressure of my nitrogen, and I need to add my pressure of oxygen, and I will add my pressure from the argon, and I'll add pressure from CO2, and I'll add my pressure from other. And that will equal my total pressure. Okay, so if we say my total pressure is 1, I need to figure out what all of these parts are. So all I need to do is take 78% and times that by 1 atm to get 0.78. So this is for my nitrogen. So my nitrogen pressure is 0.78 atmospheres. And I'm going to do the same thing for oxygen. 20.9% times 1 would give me 0.209 atms of oxygen. And same with my CO2, 0. There we go, I had to be able to see it. 0.03% times 1 gives us 0.0003 atm of CO2. Argon is 0.90% times 1.009 atms. And finally, my other gases would be 0.17% times 1.0017. And then, lastly, if I add every one of these partial pressures up, so 0.78 plus 0.209 plus 0.0003 plus 0.09 plus all of these added together, I would get 1 ATM.